Start over.
Chapter 10, Chemical Bonding, Part 2, where we predict the molecular shapes and the geometry using valence bond theory and molecular orbital theory. The molecular geometry of molecules are three-dimensional, and so we describe them in terms of geometric figures. These figures have a characteristic corner where you have a central atom and have characteristic angles called bond angles. We learned that Lewis theory predicts electron groups by placing shared pairs of valence electrons and unshared valence electrons on a single nuclei. We use Lewis theory to predict molecular shapes. And now we want to introduce you to the valence shell electron repulsion theory, or VESPR, V-S-E-P-R, resulting in a geometric arrangement where we can predict the shapes of the bond angles. So as we have our central atom with repulsions going on among the electrons, using the valence shell electron pair repulsion theory, we can look back to the Lewis structure. We know the valence electrons, we know the lone pairs of electrons, and so we can write down a Lewis structure for NO2, as there are 3 electron groups for nitrogen, 3 lone pairs, 1 single bond, and a double bond. So we end up with a basic arrangement where you have 6 bonding electron groups, and these basic arrangements results in different bonding geometries. So we can look at the linear electron geometry, for example, where we have bond angles of 180 degrees. We have CO2, or carbon dioxide, or beryllium chloride, both with having linear geometry, and beryllium is the center atom with 2 chloride atoms. For carbon, you have 2 double bonds with oxygen on both sides. Or we could have the Trigonal Planar Electron Geometry, where there are 3 electron groups, as in boron trifluoride, with a bond angle of 120. Trigonal, so you have a triangle, planar, on the plane, on the same plane. Or we could have a tetrahedral geometry, which we learned in chapter 4. Instead of being on the plane at 90 degrees, the angles are actually 109.5. And we call that the tetrahedral geometry. Then we have the trigonal bipyramidal geometry, and there are 5 electron groups around the central atom, with 2 tetrahedra that are at the base. So we say trigonal bipyramidal, and this is how it looks. So trigonal bipyramidal. We have positions above and below the central atom, and also positions on the equatorial or the axial planes. So here is an octahedron, and here is the equatorial chlorine and the axial chlorine, trigonal bipyramidal. So octahedron geometry has a bond angle of 90 degrees, where we have sulfur 1, 2, 3, 4, 5, 6 hexafluoride, each with a 90-degree bond angle. We call that an octahedron. And when we talk about molecular geometry, the actual geometry of the molecule may be slightly different because of the location of the lone pairs. We can write down, this is not quite perfect geometry because the bonds and the atom sizes are not the same as the C double bond OH, or we refer to as formaldehyde. You know that the angles between the two hydrogens are 116, and between the carbon, hydrogen, carbon, oxygen, 121.9. So what does the effect of the lone pairs actually do? They affect the bond angles, making the bond angles smaller or larger depending on, as in this case with formaldehyde, the effect of the lone pairs of oxygen. Here, the lone pairs make the bond angles between carbon, hydrogen bonds smaller than the C double bond OH. So bonding electrons are shared by two atoms, while lone pair electrons or non-bonding electrons are localized on the central atom. As for example, the lone pair, there are two electrons here in NH3, and there are 4 electrons here around oxygen, and you see the differences in the bonding angles. 109.5 for methane, for ammonia 107, and 104.5 for water. So pyramidal and bent molecular geometries do get their shapes based on the tetrahedron. When we have ammonia, the lone pair repulses and bends the angles in such a way that the lone pair occupies this part of the tetrahedron, while the 3 hydrogen atoms occupy and have a bond angle of 107 as opposed to 109.5 for the pure tetrahedron geometry. So we also can have a trigonal bent planar, such as so here's our ideal trigonal tetrahedral geometry, but this is the actual geometry for formaldehyde, C double bond OCH2. So some derivatives of trigonal bipyramidal geometry could be a seesaw shape or a T shape. And so here's some examples of a trigonal bipyramidal system, where you have the lone pair. It could be on the equatorial, so you have a molecular geometry of S1, 2, 3, 4, SF4, but you could also have SF6. Or it could be a T-shape if this happens to be bromine with 2 lone pairs. Linear shape when you have xenon Xe with 2 fluorine atoms. And when we look at the octahedral geometry, it's a result of the square pyramidal. And here is our square pyramidal shape And then when we look at a square planar, here in fact is our square planar molecule. So the electron and molecular geometries can be summarized in table 10.1 that gives us different examples and bond angles of the molecular geometry as well as the electron geometry of different molecules, all the way to the octahedral, square pyramidal, and square planar geometries. So the key is first draw the Lewis structure of the central atom, determine the number of electron groups, and then classify each group as a bonding or lone pair using table 10.1. So on the paper, we want to draw and represent the three-dimensional shapes by putting the central atom on the plane of the paper and drawing straight lines to indicate bond. And for atoms in front, use a solid wedge or a hashed wedge to designate behind the plane. So here's our carbon, hydrogens, and a tetrahedral, and then we have an O and an OH. So we have CH3OH. C is tetrahedral. The shape around C is trigonal planar, but O is a bent, tetrahedral bent. And when we describe this geometry of methanol tetrahedral bent geometry, for a molecular to be polar, it should have polar ends and have dipole moments, and therefore polarity affects intermolecular forces, and so they would have boiling points and solubilities. So if they're alike, then like dissolves like. Non-bonding pairs though affect molecular polarity, and they pull very, very strongly in this example where we have hydrogen and chlorine. Chlorine is more electronegative than hydrogen, so we designate that it's more polar and put the arrow there. So delta plus, low electron density, and delta minus, high electron density, designating chlorine as more electronegative. When we have carbon dioxide, where there is no net dipole moment, both oxygen are withdrawing the electrons equally, the net result is a non-polar molecule. When in fact you have water, which is we have a net dipole moment of delta minus here, the net result would be a polar molecule. Predicting the polarity of molecules, therefore, first we draw the Lewis structure and determine its polarity, then see if there are polar bonds or non-polar bonds, and determine a net dipole moment. Our example here is water. Water is a polar molecule, and all ionic substances, compounds, will dissolve in water and be attracted to the positive and negative charges. Molecular polarity also affects solubility. Oil is nonpolar while water is polar. And then we end up with the problems with the Lewis theory. It gives us a good first approximation but we cannot actually give and write one correct structure as a result of the resonance. For example, we have oxygen as paramagnetic, although Lewis structure predicts that oxygen is diamagnetic. So we have to turn to another theory, the valence bond theory that Linus Pauling and a few other scientists point out that the interaction depends on whether the orbitals align along the axis or outside the axis. And here we have the interaction, the potential energy diagram of two hydrogen atoms. Quantum mechanically, we can do these calculations. And then we also want to look at the molecular orbitals as two atoms approach each other. So the molecular orbitals would be more stable than the separate atomic orbitals. And so when we try to draw the formation of hydrogen sulfide, here are the two hydrogen atoms and sulfur, 3s2, 3p4. We will predict a bond angle of 90 degrees, but actually, experimentally, we find bond angles of 92 degrees. So valence bonds theory refers to the hybridization of orbitals. So if we are given carbon, the 2s orbital hybridizes with the 3p orbitals, so we end up with sp3 hybrid. So this is an sp3 hybrid orbitals, and which in fact is what we observe experimentally. The main concepts for the valence bond theory is that the orbitals can be hybridized, the chemical bond that results into a new molecular orbital. So when you combine an S and a P to form the tetrahedron methane, you end up with 1, 2, 3, 4 sp3 hybrid orbitals. Combining 2s with 2p and 2 sp hybrid orbitals, H doesn't hybridize. And so essentially these are the 1, 2, 3, 4 sp3 hybrid orbitals which can bond with the hydrogen molecule. And so this is what sp3 hybridization looks like geometrically with 109.5 degrees. And so when we represent the molecular, the orbitals, the electrons in the orbitals, we draw the four electrons in each orbital. So bonding with the valence bond theory, there's an overlap. The orbitals must either be aligned along the axis. So here are the 1, 2, 3. So 1s and the 3 p's, and when they're hybridized, we have 1, 2, 3, and the fourth one on the bottom, sp3 orbitals. To hybridize an sp2, we get an s and 2 p's, and we have 120 degree bond angle, and so we have 2 p's, right? So then to form a pi bond, and sp to form a sigma bond. And the Lewis structure of formaldehyde looks like this, and here are the hydrogens giving one electron, and then the hybridized sp2, and then of course a double bond, one pi bond, and then one sigma bond. So these are the pi bond and then the sigma bond. So we can have either a sigma bond or a pi bond. Sigma bonds are stronger than pi bonds. The orbital diagrams, there's an overlap between a hybrid orbital, and you see the overlap as we go on. Hybrid orbital overlap to form a sigma bond. Unhybridized form the pi bonds or p bonds. Bond rotation, because there's only sigma bonds can rotate while pi bonds cannot rotate. They are fixed. Sigma bonds can rotate, pi bonds do not rotate, cannot be rotated. Now, sp hybridization is where you have two electron groups, linear in shape. You have a sigma pi bond with two pi bonds between carbon and nitrogen. Remember, the other electron that carbon has bonds with hydrogen, so you have an s orbital from hydrogen with an sp orbital from carbon and an sp orbital from nitrogen to form the pi bond and sigma bond, and then the two pairs of electrons form the pi bond. So you have a triple bond, 1, 2, 3, two pi bonds and a sigma bond. So how does the sp orbital form? You take a sigma orbital with a px, you hybridize them to form the sp orbital. And to form acetylene, here is an example of 3 double bonds, a sigma bond in the middle and 2 pi bonds, one above and one below. And to form a dsp3, we take a d orbital and hybridize it with an s orbital along with a 3p orbitals to form a trigonal bipyramidal geometry. And as we, here's the d orbital with the 3 p's to form the dsp3 hybridized orbital. To form the d squared sp3 orbital, then we take 2 d's and an s and a 3 p's to form the d squared sp3 orbital. So predicting hybridization and the bonding, we again start with the Lewis structure, then you use the Vesper theory to predict the electron group. And then we select the hybridization scheme that matches the electron group, and then we label the bonds as sigma or pi. Problems though with a valence bond is that there are still properties that it doesn't predict perfectly. An example is the magnetic behavior of O2. Valence bond presumes that the electrons are localized in orbitals, but it doesn't account for the delocalization. So then we go to the third theory, molecular orbital theory, and apply Schrödinger's wave equations to the molecule to calculate the set of molecular orbitals, and we construct a linear combination of atomic orbitals, LCAO, to denote a bonding molecular orbital or an anti-bonding molecular orbital. bonding, antibonding, which will have destructive interference for antibonding and constructive interference for the bonding orbitals. Electrons in bonding MOs are stabilizing, while in antibonding are not stabilizing. So properties, we can calculate the bond order of different orbitals by taking the number of bonding electrons and subtracting the number of bonding electrons and dividing it by 2. And so if we were to make a hydrogen molecule, we have 2 hydrogen atoms, and both electrons would be in the bonding orbital. And there are all sorts of different interactions between the p orbitals. And if we wanted to write down some, look at oxygen, here's boron here and here's oxygen, we can actually show that oxygen is paramagnetic because it has unpaired electrons. And although oxygen can be described by Lewis and the valence bond theory, it doesn't explain its magnetic properties, but molecular orbital theory explains its magnetic properties. So if we take a look at another molecule, a heteronuclear, that means you have an N and an O, 2 different atoms to form the NO molecule. Shows more electron density near the O because of the 2s atomic orbital, as we learned in chapter 8, that more of the electrons will tend to spend its time there. Likewise for HF, we have the HF molecule, 2 electrons in the bonding, and so we have 1 for the hydrogen atom, and for F we have 2, 4, 5 electrons, and as we fill the molecular orbitals, and so we have the HF molecule. So when we have a polyatomic molecule like ozone, O3, we can initially start out writing the Lewis structure and then come up with a molecular orbital that looks like this ozone O3 geometry. And so next class, students will be lecturing on chapter 10 and talk about the different sections on molecular shape and polarity, the effect of lone pairs predicting molecular geometries, and consider the different bonding theories. Okay, that's it. Thank you.